Hello everybody, myself Prashant Mukhopadhyay, faculty member, Electrical Engineering Department, Kerala Kolkata College of Engineering and Management. So in the last class of our induction motor, we were discussing about the different starting methodologies of three-phase induction motor. And we have covered all the methods of starting say for the squirrel cage induction motor. So that is starting from the dual starter to say primary resistance starter, then auto transformer starter, and then star delta starters. And we have also discussed about the different working of these starters and their relative advantages, disadvantages, etc. And only the leftover portion was the starting methods of the slipring motors, slipring induction motors. And today we'll discuss this starting of three-phase, say cage rotor type or slipring induction motors starting. And after that we'll discuss about the speed control of the three-phase induction motor. So let us start with the slipring motors starting methods. So actually slipring or wound rotor type induction motors are basically started with rotor rheostat or rotor resistance starters. So to limit the rotor current, which consequently reduces the current drawn by the motor from the supply, the resistance can be inserted in the rotor circuit at start, and this addition of the resistance in the rotor in the form of a three-phase star connected rheostat, and that is shown. This arrangement is shown here. This is the stator, and you know this is not likely the primary resistance starter in case of squirrel cage induction motors. So in that case, external resistance are connected with the stator circuits, stator windings. But here, in case of slipring or wound rotor type three-phase induction motors, so this external resistance is connected to the rotor side. So that's why it is for rotor resistance control. Actually, rotor resistance or rotor rheostat starter. So basically, say star connected external resistance box is connected to the rotor sides through the slip rings of the rotor. So this is set, and this is a slipring type rotor. So slip rings are provided at the rotor shaft, and the external three-phase rheostat, the star connected rheostat is connected to the rotor through this slip ring. Okay, so as a result, the rotor resistance will be enhanced, and the initial current will be reduced. Okay, so this external resistance is inserted in each phase of the rotor winding through slip ring and brass assembly. That is shown here. This is the slip ring and these are the brass. And initially maximum resistance is in the circuit is inserted basically at the initial conditions, and as the motor gathers speed, that is around 70% to 80%, the resistance is gradually cut off, and the operation may be manual or maybe automatic. So the starting torque is proportional to the rotor resistance, and the advantage of this type of starter is not only the starting torque is limited, but the starting torque of the motor also gets improved. Okay, but limitations is it can be used only for slipring induction motor, as in squirrel cage motors the rotor is permanently short circuit. This is not possible for squirrel cage induction motor to use external resistance to connect the rotor circuits because the squirrel cage induction motor are short circuited. Okay, so this is only it is limited only to use in case of slipring induction motors. So with this we can say conclude our discussions on the different methods of starters for squirrel cage as well as slipring induction motors or three-phase induction motors. Hope all of you have understood it. So if you have any queries or any questions, you may ask me through mail, phone or WhatsApp. Okay. So we'll go to the next topic right now, that is speed control of three-phase induction motor. So actually speed control can be done either control from the stator side or control from the rotor sides. So if we take this think about the speed control from the stator side, so first of all we have to know the how we can control it. So we can control by changing applied voltage, okay, by changing the applied frequency, or by changing the number of stator poles. So these are the three methods to control the motor speed from stator side. And other three methods are also can be used for control the speed, that is the control from the rotor sides. So it can be either by rotor rheostat control or by operating two motors in concatenation or cascade, or by injecting an EMF in the rotor circuits. So actually in the stator side there are three possible way of speed control. In the rotor side also there are another three possible methods of controlling the speed of three-phase induction motor. Okay, so we'll so one after another we'll discuss. First up, we will discuss the speed control from the stator sides. Let us start with the stator side. The first method, that is by changing the applied voltage. See, actually, if we see the torque equations of the three-phase induction motors, we can find that the torque is directly proportional to S E2 square R2 by R2 square plus S X2 whole square. Okay, you know all these parameters are known because see, this is torque, S is the slip, E2 is the rotor induced EMF at standstill, and R2 is the rotor circuit resistance, X2 is the rotor circuit reactance, and S is the slip, as I told you. So this rotor induced EMF at standstill, that is E2, depends on definitely the supply voltage, and so we can write E2 is directly proportional to supply voltage V. And for low slip region, that is this portion, that's Sx2 whole square, so is very small in comparison to R2, the rotor resistance. So hence we can write, we can neglect this, so we can write this torque is proportional to, if we put E2 by V, since these are directly proportional, so S V square R2 by R2 square. So that means it is coming to, so S V square by R2. So if R2 is constant, that is rotor side resistance, so then it will be directly, the torque is proportional to slip time V square. Okay. Now if supply voltage is reduced below rated voltage as per these equations, torque produced also decreases. Okay, see, as torque is directly proportional to S V square, if this V is reduced, that means torque is reduced. Okay, so this is another way by changing this applied voltage you can control the speed. Okay, but if supply to supply the same load, it is necessary to develop same torque, hence value of slip increases, so the torque produced remains the same. Okay, so actually if the load is unaltered, load is same, so in that case reduced supply voltage means reduced torque. So in that case, that is a problem. So how we can control this or manage this? So we can manage it by increasing this slip. Okay, so if slip is increased, in that case this torque will be increased, and as a result by reduced voltage and increasing this slip, torque can be say controlled in such a way so that same load can be say serviced, or same load can be catered. Okay, so sleep increases means the motor reacts by running at lower speed, simply. So as you know, sleep is the difference between the rotor speed and the synchronous speed with respect to the synchronous speed. So sleep increases mean this you have to sacrifice the rotor speed. Okay, so so motor produces the required load torque at a lower speed. Clear? So that means if we want to cater the same load with reduced voltage, so in that case you have to increase the slip, and increment of slip means the sacrifice of speed. Okay, so that means the motor will cater the same load torque at, or service serve the same load torque at a lower speed. So this method, though the cheapest and the easiest, but it is rarely used because large change in voltage is required for a relatively small change in speed. Okay, and due to the reduction in voltage, current drawn by the motor increases, and so due to this increased current, the motor may get overheated. So this large change in voltage will result in a large change in the flux density, and thereby seriously disturbing the magnetic condition of the motor. Okay, so these points are to be kept in mind very sincerely, because this reduced voltage will say change for say this large change in the reduced voltage will change as very small change in the speed, and due to this large reduction in the voltage may so current drawn by the motor will be increased, and due to this increased current, the motor losses will be more, and that is the motor will get overheated. So this large change in voltage will result in a large change in the flux density, and thereby seriously disturbing the magnetic conditions of the motor. So actually that's the very reason for why this though this method is very cheap and easy, but it is rarely used. Okay, so this is the actually say from the stator side, by changing the applied voltage we can change the speed, but a large change in the applied voltage will change a very nominal speed, and as also the motor will get overheated due to the current run will be more due to reduced voltage, and that's why though this method is cheap, easy, but still it is rarely used, and because this also actually disturb the large change in the flux density, and so magnetic conditions of the motor will be largely disturbed, and these are the very reasons for why so being one of the cheapest and easiest method of speed control, this method is rarely used. Okay, so this is the first method of speed changing by controlling from the stator side, that is by changing the applied voltage. Okay, so now I will discuss about the speed control by changing the applied frequency or supply frequency, or commonly known as V by F control. So whenever three-phase supply is given to the three-phase induction motor, a rotating magnetic field is produced which rotates at synchronous speed, and that synchronous speed can be given by Ns, actually equal to 120 F by P. And this F is the supply frequency and P is the number of pole of the motor actually. So in three-phase induction motor, EMF is induced by induction, similar to that of transformer, which is given by the induced EMF E or V equal to 4.44 phi k T into F. And therefore this phi will be V by E or V by 4.44 kTF, and this K is the winding constant. Okay, T is the number of turns per phase of the winding, and F is the frequency. So if we change this frequency F, then this synchronous speed will also change. Okay, but with the decrease in frequency, flux will increase. Okay, if we decrease this, then this phi will increase. Okay, and flux will increase, and this will change in the value of the flux. Actually this change will causes the saturation of the rotor and the stator poles. So that is the saturation of the magnetic circuit basically, which will further cause increase in no load current of the motor. Okay, so that is the case, and this is the reason. So so this should be taken into consideration. Actually, to maintain the flux phi constant, so what are the methods? So this is constant, only these two. So you have to maintain this ratio V by F in such a way so that this flux is constant. So that means, so it is possible actually if we change the voltage, or if we decrease frequency, flux increases, but at the same time if we decrease voltage, flux will also decrease. Okay, and causing no change in the flux, and hence it remains constant. Okay, so this is a very typical thing. So that is if we decrease voltage, flux will decrease, so causing no change in the flux, and hence it remains constant. If we decrease frequency, flux increases, but at the same time if we decrease voltage, flux will also decrease, and as a result no change in flux, and hence it remains constant. So here we are keeping the ratio, this V by F, as constant. We can say we maintain the or control the speed, and so hence its name V by F method. For controlling the speed of the three-phase induction motor by V by F method, we have to supply variable voltage and frequency, which is easily obtained by using converter and inverter set. So basically you will already you are familiar with the converters, and also you have heard the name of the inverters, so in your power electronics class, and that is also being taught in this semester itself. So I think you don't have any problem with this terminology, this converter and inverter set. And if we say discuss, it will be clear. So the normal supply available is our system is a constant voltage, constant frequency AC supply. So this is the normal available supply. So the converter will convert this AC supply into DC. Okay, and then this DC is again given to the inverter. So DC will be then converted to AC. Okay, so this Inverter will then convert DC to variable voltage, variable frequency AC. Okay, so actually by selecting the proper frequency and maintaining VYF constant, smooth speed of the induction motor is possible. Clear? So actually supply frequency, by changing supply frequency we can change the speed, but there is a problem. So by changing supply frequency we have to sacrifice the flux. That is we have to say if F is decreased, phi will increase, and that will make the saturation of the stator and the rotor cores. In that case, if we say again decrease this V, then flux will be flux will also be reduced. But you have to control this V and F in such a way so that this flux is constant. Okay, so that can be that's why this method is called VYF method. So, and that can be possible only by using converter inverter set. Actually, by since our supply system is a constant voltage, constant frequency supply. So firstly we will convert this AC supply into DC, then convert this DC with the help of the inverter with in variable voltage and variable frequency AC, and by injecting this variable voltage, variable frequency AC to the stator winding of the induction motor, so we can control the speed. Okay, so this is the schematic diagram. This is AC input, constant voltage, constant frequency, and this is converter. Basically this convert this constant constant voltage, constant frequency AC to DC, and then DC will invert this this DC will be inverted by this inverter we at variable voltage, variable frequency AC supply, and then it is supplied to the stator of the induction motor, and as a result the speed will be controlled. But what is the disadvantage of this method? Definitely it is used where the induction motor is only load on the generators, range over which the motor speed may be varied is limited. The supply cannot be used to supply other devices which require constant voltage. So that's actually, if it is a dedicated system only, so for a particular motor, so then it is okay. But if the supply system is connected, other equipments and are also connected, so where the constant voltage, constant frequency is required, so in that case this is not possible. So, and another thing is the range over which the motor speed may be varied is also very limited. Okay, so this is another method from the stator side. By changing the applied frequency or supply frequency, the speed can be controlled, commonly known as this is the VYF control, or variable voltage, variable frequency VF control. Okay, so this is another one, and the third one is by changing the number of stator poles. So let us see what is that. Now actually by changing the number of stator poles, this method actually known as the pole changing method of controlling the speed. So in this method actually it is possible to have 1, 2 or 4 speeds in steps. So by changing the number of stator poles, continuous smooth speed control is not possible by this method, and this is very important. This since the change of the stator poles can be either in 2, 4 or 6 like this. So speed also will be changed since speed is 128 by P. If P is 2, the speed will be something. If P is 4, speed will be something. and if it is 6, speed will be something. So but in between 2 and 4, so there will be no control. So basically speed can be changed only in a step. Okay, so this is not a smooth speed control. So that's why by pole changing we can get a speed changing in a step way method, not by smooth or continuous method. And the status pole can be changed either by consequent poles method, or by multiple stator winding methods, or by pole amplitude modulation methods. So there are three methods. One is consequent poles method, second is multiple stator winding method, and third is pole amplitude modulation method. So just today we'll just discuss in say just nutshell. In the next class we'll discuss in details of this pole changing method. So let us firstly have a quick look out of this three methods if possible. So let's say consequent poles method. So in this method, connection of the stator winding change with the help of simple switching. So due to this, the number of stator poles gets changed in the ratio of 2:1. Hence, either of the two synchronous speed can be selected. Okay, and once again I'm telling this method, connection of the stator windings is changed with the help of simple switching, and due to this, the number of stator poles gets changed in the ratio 2:1, and hence the two synchronous speed can be selected. So considering pole formation due to single phase of a three-phase winding, so that is shown here. There are three tapping points to the stator winding. The supply is given to two of them, and the third is kept open. Here it is. See. Okay. The current in all the parts of the stator coil is flowing in one direction only. See. Okay. So this is the case. Okay. So actually the current in all the parts are flowing in the same direction. So due to this, 8 poles get formed. So actually this is another one pole. This is south pole. So this is north. Then south, north, south, north, south, north. So how many poles are we are getting? Say 2, 4, 6, 8. 8 poles we are getting. So how many? What is the speed can be possible if it is a 50 Hz supply? So 120 F, that is into 50 by 8. So how much it is coming? It is 750 RPM. Okay. So if two terminals to which supply was given earlier are joined together, and supply is given between this common point and the open third terminal, the poles are formed as like this. Okay, so it is joined here, two terminals. These two terminals are joined. So how many poles are there? So there you are getting, say, south, north, south, north, and south. So actually it is 4 poles. Okay. Though it's actually 4 poles, so the direction of current through two coils is different than the direction of the current through the remaining two. So thus the upward direction is forming if it is a south pole, and the downward direction is the north pole. Okay. So in this case the 4 poles are formed. So the synchronous speed possible is 1015 500, that is 1500 RPM for 50 Hz frequency. Okay. But the disadvantage, the speed changes in step and smooth speed control is not possible. Okay, and so disadvantage of this type of methods of this speed control is that speed change in steps and smooth speed control is not possible, and this method can be used only for the squirrel cage type motors, as squirrel cage rotor adjusts itself to same number of poles as stator, which is not in case in slipring induction motors. This is very important because squirrel cage type motors basically adjust itself to the same number of poles as stator, and, but it is not possible in case of slipring induction motors. And mostly this type of speed changing is applicable in case of elevators, traction motors, and small motors to drive machine tools. Okay, so actually this consequent pulse methods, so more or less this is the stator windings are changed with the help of simple switching, and number of stator poles gets changed in the ratio of 2:1. Initially it was we have discussed in 8 poles, so it will be as 2:1 it will be say 4 poles. So hence either of the two synchronous speeds can be selected. So consideration a three-phase single due to a single phase of a three-phase winding, it is shown. Basically this is for 8 poles for 750 rpm, and when this two terminals of supply was given earlier, joined together, and supply is given between the this common and the open third terminals, this way we'll get actually the poles are formed like this. Okay, and the speed will be changed to say 150. The number of poles will be 4, so it will be 150, 1500 actually, 1500 rpm. So with this speed can be, as I told you, this disadvantage is speed change in steps, and smooth speed control is not possible, and also that it is suitable for squirrel cage induction motor, as its rotor adjusts itself to the same number of poles as stator, and mostly used in case of elevators, traction motors, and small motors to drive machine through. So that's all about the method of say consequent poles method. Okay, so thank you all for your patient hearing.